Hello everyone. In the previous session, I did mention that tensors are the building blocks of PyTorch framework. So whatever data that we are considering to present to the neural network, we are converting them to numerical data. So be it image data or be it waveform data or be it text data, any form of unstructured data or structured data as such, we are representing them in the form of numerical data, which are nothing but tensor objects. So before we get into this particular coding exercise of creating the tensor objects and try and look at what different mathematical operations that we can perform by leveraging all the objects that we have created, let us look at this particular MLP architecture where we have this input layer where we present our input data to the network, and there are two different hidden layers and one output layer as well. So all the data, all the input data that we are presenting is represented in the form of tensor object. So this is numerical data. Let's say that we have a set of images, which is our input data. So this unstructured data, we are converting them to tensor objects. So if it's a grayscale image, if it's going to be a grayscale image, we are converting this to a 2D tensor. If it's a color image, we are going to convert that to a 3D image, 3D tensor. Even the weights that you are observing, the weights that are associated with all of these different inputs that we are receiving from the previous layer, all these weights can also be represented in the form of tensors. Even the output is represented in the form of tensors. So any mathematical calculation that's being conducted during the forward propagation of the training process is essentially the operations that are conducted on different tensors. Let's say that we are looking at computing the sum of weighted inputs. So summation of I equal to 1 to j wi xi plus bias. So this is a more generic form of what you are computing at this particular very node or at this particular neuron here. We're just taking the weighted sum of previous inputs or the weighted sum of inputs that we received from the previous layer, and we are also adding the bias term associated with this particular neuron here. So this is z that we compute. So in order to understand this computation a little better, we look at this simple perceptron. The simple perceptron here is a single neuron model which basically considers these different inputs x1, x2 and x3. x1 is associated with salary, x2 denotes EMI and x3 denotes other income. We have values pertinent to each and every variable. And there are weights also are associated with these different x variables. And now what we are doing is to compute the value of z. The value of z is nothing but the weighted sum of all of these inputs. So x1 multiplied by 1, x2 multiplied by 2, x3 multiplied by 1. So when you do this computation, so 80,000 multiplied by 1 is resulting in 80k, and this here minus 10k multiplied by 2 is resulting in minus 20k, and x3w3 is resulting in 20k, and the cumulative sum is resulting as 80k or 80,000. And since the z value is going to be this 80,000 plus bias is minus 40,000, as we can clearly observe from here, the resultant value of z is going to be 40,000 as we have represented here. So now z that we have computed, the value of z is being passed as an input to your activation function that you have defined. The activation function can be anything. In this particular example, it is a step function. So when it is a step function, having a value of z which is greater than 0, you typically observe the y value to be or f of z value to be 1. So the value of f of z here on y-axis is 1. Whenever you observe that the z value is greater than 0. If z value is lesser than or equal to 0, the value of f of z is going to be 0. So it's binary. So you either observe 1 or 0 in the output here. F of z is always going to produce 1 or 0, especially when you are considering step function for your activation function. Okay, we'll deal with different types of activation functions later. For those who have covered the previous module, we already have covered all the different activation functions in depth. So now, since we have gained an enough understanding on what is a mathematical operation that just gets computed in your forward propagation, we are now going to do those operations by considering these different tensor objects. Weights represented as tensors, biases represented as tensors, inputs and outputs are also represented as tensors. We clearly understand how significant tensors are in the whole process, in the whole model training process now. So let's get back to this particular coding exercise wherein I have imported all the necessary libraries. I have imported NumPy, PyTorch library, which is Torch, and then Matplotlib as well. I have mounted the Google Drive. Maybe I would want to access certain files which are already present in my Drive folder. Now let's create different dimensional tensors. Tensors can be of any dimensions. It can be a 0-dimensional tensor, or it can be 1-dimensional tensor, 2-dimensional tensor, 3-dimensional tensor, or it can be n-dimensional tensor as well. For simplicity, let's look at the process of creating a tensor. So I make use of this particular function from Torch module, which is tensor, and provide a scalar value. I'm providing a scalar value of 1, where we are essentially going to create a 0-dimensional tensor now. When you look at the data, or when you inspect the data, you clearly understand that this is a tensor object. Even when you look at the type of this particular object that we have created, we know that it's a tensor object. So the number of dimensions of this particular tensor object is going to result in a value of 0, since this is a 0-dimensional tensor. I can also create a 1-dimensional tensor. I'm changing this particular variable name. 1-dimensional tensor can be created by providing a list of possible values within the parentheses here. You can also specify the d type, but we'll specify that later. And you can check the type of this particular tensor object, which is data underscore 1D. And we also can look at the data type. The data type is going to result in int32 or int64. It's torch.int64. You can explicitly state the data type here as d type is equal to torch.int64. We can also specify it as float64. Even if the values are integers, now all the values within this particular tensor object are going to get updated to floating point values, since we have explicitly stated that the data type should be of floating point. Okay. Later, you can also inspect the different attributes like n dimensions, like what are the number of dimensions. So there are only 1 dimensions here, since it's a 1-dimensional tensor object. You also can look at the size of it and check the size of it. Size of it clearly provides a value of 4, since there are 4 elements present in this 1D tensor object. What if I change this particular data type to int64? I still go about providing some floating point values here. So now let's actually rerun this code so as to understand what is the d type now. The d type should be int64. The resultant values that get stored in this tensor object are now integers. So all the decimal points are ignored, since we are explicitly stating that the d type should be of int64 and not float. Okay. In order to look at the different data types that are possible, you can always reference the documentation. It's always a good practice to look at the documentation whenever you are in doubt. So there could be many data types that are possible, like 32-bit floating point, 64-bit floating point, which we have used just now, unsigned integer and signed integer, 8-bit unsigned and 16-bit unsigned, and so on. You also can represent complex numbers using complex 32 or complex 64. You can go through all of this documentation, revert back to us in case of any questions there. Okay. We have inspected few of the attributes associated with this object, and we also have invoked certain methods like size and all, and we have understood the functionality of it. You can explore many more attributes and methods by making use of this dir function. This dir function produces the list of all possible attributes and methods here. So now let's go about creating a 2-dimensional tensor. So 2-dimensional tensor will have more or less the same values or similar values provided as list within a list. So I'm just also providing this outer square braces so as to indicate that this here is going to be a 2-dimensional tensor object. So checking n dimensions will generally produce the number of dimensions associated with the object here. Okay. Now I can also create a tensor object from a NumPy array. So I am generating sequential data. np.arrange is going to generate the number starting from 0 to 9 with a step count of 1 here. So this here is a NumPy array. I am going to make use of torch.from_NumPy function in order to convert this NumPy array into a tensor object. You can see that this particular T object that we have created is nothing but a tensor object. I can reshape this 1-dimension tensor into 2 by 5. You just need to make sure that the number of rows and columns that you're supplying just matches well with the total number of elements that are present in your one-dimensional tensor. That's all. Reshape functionality is pretty much the same as we have dealt with in our NumPy sessions. Instead of reshape, you also can try out view. It's going to produce the same result to you. So we have explored on how we can create zero-dimensional, one-dimensional, two-dimensional tensor objects. You also can create three-dimensional tensor objects by providing another outer square bracket. This time, I'm just stacking two-dimensional tensors on top of each other. That's how you can visually represent them or visually imagine them to be. So now if you look at this way, if you consider this visualization, so this is one two-dimensional tensor object and this is another two-dimensional tensor stacked on top of each other, which do have indices as well. So 0 points to this first two-dimensional tensor and 1 points to the second two-dimensional tensor. And later when you are referencing any given two-dimensional tensor of this 3D tensor, you can still go about accessing row indices as well as column indices to perform indexing and slicing operations. We have not dealt with indexing and slicing operations yet. If we look at this two-dimensional tensor, we clearly have this data and we can perform indexing and slicing operations in pretty much similar manner like we have done for our NumPy arrays. So let me change this data a little bit in order to distinguish these two different rows. So 10, 12, probably 30 and 41, just providing some random data. And now in order to reference the first row within this particular square braces, I am providing an index of 0, comma. If at all I want to select only this highlighted data, I am looking at column index 1 till column index 3, but the column index 3 is always excluded. So 1 column 3 is going to produce a result of 2 comma 3. So this is what I try to retrieve and I'm able to perform the slicing operation. I can also retrieve 12 comma 30 along with 2 comma 3 by just providing column 1 here. Just copy paste this whole statement, provide 0 colon 1 so that you are now able to see, 0 colon 2 because 2 will always be excluded. 2 comma 3 and 12 comma 30 are what we are now selecting from the overall data that you have. So I'm leaving it as an exercise to you to further explore on different indexing and slicing operations. So it's pretty much remained the same. There's no difference at all in terms of the slicing and indexing operations that we already have dealt with during our NumPy sessions. We essentially have looked at converting this NumPy array into a tensor object. So we can also do that. We can also convert this tensor object back to NumPy array by just invoking this method called NumPy. So now this is a NumPy array. You also can convert this to a list object by using toList. So you essentially have converted a NumPy array or created a tensor object from a NumPy array. So this was a NumPy array initially. You converted this to a tensor object. You later have used this method .numpy. This is .numpy in order to convert it back to a NumPy array. You also have converted this tensor object to a list object by using toList. So this is a list object. So these are the different operations or different methods that we can leverage in order to convert NumPy array to a tensor object and vice versa. Okay. And you also can convert a tensor object to a list object as we have seen so far. But why don't we use NumPy arrays in place of tensor objects? So what is the significance of using tensors over NumPy arrays? Tensors essentially has got two additional capabilities, one of which is the ability to run on GPUs, which NumPy arrays does not have. So while creating this tensor object, you explicitly can provide an additional parameter called device, asking this operation or asking to push this particular tensor onto the GPU. So you can essentially perform these mathematical operations that you ought to perform on GPUs, where using NumPy arrays, it's not possible. You also have this additional parameter called requires grad. So setting requires grad equal to true helps us in computing the gradients during the backpropagation process. For those who are not aware of backpropagation, it's totally fine because we are going to deal with it much later. So during backpropagation, it's always essential for us to compute the gradients. The gradients are in turn used in order to minimize the overall loss. Let's not get into complete details as of now. For those who have covered the previous module, you're already aware of it. So requires grad is one such parameter which is going to help us automatically compute the differentiations and produce the gradient values for us. So these are two major differences in between a tensor object and a numpy array object. So considering tensors are basically going to help us increase the execution speed. Okay. Also, it's going to help us in reducing the computational complexity. We need not explicitly compute the gradients. It automatically computes the differentiation and produces the gradients for us during the backpropagation. Okay. So apart from this, I also would want to discuss on how we can convert this image data into 2D tensors and 3D tensors like I've discussed with you a while ago. So a grayscale image, as I have mentioned, will be essentially converted to a 2D tensor. So let me actually use this im function, im read function, and provide a relative path here. Providing a relative path, which is drive, my drive. I'm just looking at this particular path here, these directories, and then trying to identify what could be my relative path. So digit underscore 8.png is the grayscale image that I have already saved in my drive. So now I am assigning this to something called digit underscore data, and torch.tensor is what I'm going to use to convert this digit data into a 2D tensor object. You can check the type of this particular resultant object so as to make sure that it's a 2D tensor object or not. So you can check the n dimensions as well so as to see if this is a 2D, if this is two-dimensional or not. Okay. So similarly, you also can read this color image, the color image, and you also can verify if the tensor that you convert it into is a three-dimensional tensor or not. So dog image is one such file that I have placed. I can replace this with dog underscore img dot jpeg. And now I can write it as dog underscore data and use this within the parentheses and call it as data underscore 3D now. And then further look at data underscore 3D dot endim. This should be dog underscore img. Okay. So we now understand that this is three-dimensional in nature. We also can check the shape of it as to look at the dimensions in total. And now we are also looking at printing out this particular plot, representing this particular data in the form of a plot. Just wanted to make sure that this is a color image or not. So plt.imshow is a function that's going to help us. I use this data underscore 3D that we already have written data to, and then use plt.show so as to plot this particular or print this particular data out and see if this is a color image or not. So this here is a color image. So we essentially have looked at considering a grayscale image and represented that as a two-dimensional tensor, and also considered a color image like what you're observing now and represented it as a three-dimensional tensor now. So we have a good overview on tensor objects, on how you create tensor objects, what are the different dimensions that are possible, and we have looked at creating 0D, 1D, 2D, and 3D tensors. You can extend that to any number of dimensions. We have also looked at different data types. We have performed indexing and slicing operations, but we have not yet looked at doing any mathematical operations on different tensor objects that we have created, which will be the subject of discussion in our next session. Okay, so that's all in this particular session. Thanks for watching.